Yeah, if I could, it's a couple of you asked me if I can change their grade on archive. I'm not 100% sure how to do that. So I'm gonna try to figure out how to do that, and then I'm gonna email everyone. And if you want me to change your grade for some reason, you can let me know. But currently, I'm not 100% sure how to change the grade. Okay, so we're gonna continue today with quadratic surfaces, and in general, these are surfaces written in this form. So the easiest surface to try to understand, I think, is the ellipse, and we've seen it multiple times. And generally, when we were writing, if we're writing a sphere centered at some point, then like we saw in the test, we would have if the center of our point is let's say the center of our point is a BC, then the sphere would be x minus a squared plus y minus b squared plus z minus c squared is, let's say, equal to r squared. Okay, so that was generally for a sphere centered at some point. In general, when dealing with an ellipse, we're going to have that well, now we're not talking about the center. So let's imagine that this ellipse is centered at the origin. So we're going to have x over a squared plus y over b squared plus 0 over c squared is equal to 1. So let's try to understand what this equation is telling us. And the way to do it is by drawing our axis. So here's our x, and here's y and z. And then trying to understand what kind of shapes we get when we restrict our ellipse in different dimensions. So let's just first start with the z dimension. What happens if z is equal to 0? So if z is equal to 0, you get this over here is equal to 1. So that's when z over here is equal to 0. And this would be the equation of an ellipse in 2 dimensions, with an x-axis having the radius or whatever the axis A, and then having a smaller axis in the y direction which would be B. So, or bigger, doesn't really matter. Anyway, so you would have something like this. Now notice when y over here is 0, which happens here. So when y over here is 0, we have x squared over a is equal to 1, which means that x squared is equal to a squared, which means that x is equal to a, which means this over here is a. And this over here would be b. Okay. That's what happens when z is equal to 0. Now, when z is equal to 1, well, 1 second. Okay, let's try, let's say, a half first. Well, it doesn't really matter. It's depending on c over here, but Okay, whatever. Okay, let's just do 1. Why not? Okay, so when z is equal to 1, then you're going to have that this side over here so you're going to have x over a squared plus y over b squared is equal to 1 minus 1 over c squared. Now, depending on what c is, this is some number. And if this number ever becomes negative, then we're done, because then these two sides are never equal, so you don't have points that get those numbers. But so long as this number over here is positive, then this makes sense, and we're looking at different, and in general, this would be z0. So in general, this would be some z0 that you choose, some fixed number, 1, 2, whatever. And as long as this thing is positive, these are equal, and you get smaller and smaller ellipses as this thing, as c, well, in this case, sorry, as z0 becomes bigger and bigger and bigger, gets closer and closer to c, this thing gets closer to 0, and your ellipses get smaller. So you're going to get, as you go along the z direction, you're going to basically get smaller and smaller ellipses. So you can imagine an ellipse like that, and then you can imagine a smaller one, and then a point. And same thing happens in the other direction. And a point. Now, this isn't drawn perfectly, but it would end up looking like an ellipse. So whatever. I'm not sure this would come out that better, but, and in the x direction, this is a over here, and this over here is b. That's the y direction, and this over here is c. Now, there are other ways of looking at the same thing, which is by fixing your y, so looking over intervals in the y direction like this, and seeing how the xz direction ends up looking, and you would get ellipses in those directions too, because you would get this plus this is equal to 1 minus this, with y being fixed, so that would go right over there, same exact thing, and you would get ellipses like this, and they would grow and then shrink and a point. Any questions about this?
Can you explain that last part one more time?
Yeah, so I was currently dealing with a situation where we look at z being fixed. But you can do the same thing with y. So you can say, oh, what if I want y is equal to 0? What do I get then? So y is equal to 0. Then our equation becomes x over a squared plus z over c squared is equal to 1. So what is this? In the xz direction, in the xz plane, so that's when y over here is 0, so that's over here, we get an ellipse. So that gives you an ellipse, like that. Yeah? Did that explain it?
Yeah, thank you.
In every direction that we look at, if we fix any one of these, we're going to end up with an ellipse. And that's what gives us an ellipsoid. So an ellipsoid, every direction that we cut this thing, so here's what we have, and every direction we cut it, we get a circle, an ellipse. If we cut it in the horizontal direction, we're going to also get an ellipse. So that's what they're showing here. They're taking a plane and they're cutting it, and they're looking at the trace, and they're cutting it at z is equal to z0 at some constant z. Okay. So when they cut it, they get, and they're trying it for specific numbers. Oh, so they're saying trace find the traces of the ellipsoid of this one. So in the xy direction, so that's going to be here xy. So z is equal to 0. So in this case, z is equal to 0. So then we get this equation is equal to 1 with the z being equal to 0. Now this is a ellipse in the xy plane, and it's this ellipse over here. And in the x direction, we have 5 over here. And in the y direction, we have 7. Right? So here, 5. So the b over here is our 7, and the well, I guess, yeah, the a over there. And then this over here happens when we set x is equal to 0. So then when x is equal to 0, we are looking at this ellipse, the one that goes under. And then this is when we set y is equal to 0. And that's this ellipse over here. So here they're showing you the different ellipses that come out. This one over here, which again, this is over here 5, and this over here is 9. So 5 and 9. Okay. So now going on to the next surface, we're going to look at the hyperboloid, and there are two types. There's the hyperboloid of one sheet, and the hyperboloid of two sheets. And it's easy to remember which one you're dealing with, because okay, first what you do is, instead of having the x, the y, and the z all positive on the same side, you put the z, or the direction, which is not exactly elliptical. So 1 second. If this thing over here is 0, then this is an ellipse. And it doesn't really matter what this is, we get different ellipses. And those are the directions where you have ellipses, like that. That's the z direction. As z changes, you get different ellipses. So that's over here, x squared over a plus b, y squared, y over b squared is equal, and then you're going to have, let's say, z0, so some constants that are changing over c squared plus 1 or minus 1, but let's do plus 1 first. So then you get ellipses going up and down this thing. Now, the only real interesting thing happens when the z is not the constant. It happens when one of these are the constants. So let's just do the one for y. If y is the constant, then we're going to get x over a squared minus z over c squared is equal to y naught over b squared plus 1. And this is a hyperboloid because this is minus. So now when we have the y coordinate set to 0, it's going to be in the y planes. In different y planes, you're going to have different planes over here cutting this thing. And as you do, you're going to get different hyperboloids. So in this case, you're going to get this, something like that. In order to see it better, here you can see this over here and that. So this is the hyperboloid that comes out when you set the x, when you take different x constants, and then there's another one in the y, another bunch in the y direction. So those are the y directions. So and here are your ellipses. So you have ellipses in the z direction, and this is how it all looks together. And this is the hyperboloid of one sheet, because you see it's only made out of one. If you're dealing with an hyperboloid of two sheets, well, that generally happens when you have a minus over here, because this side over here is positive. Now, if this side over here is negative at any point, then these two sides can never agree, so you just don't have those points. So when is this side negative? This side is going to be negative for any z where you're going to have that z over c is less than 1. Right? If it's less than 1, then when you subtract by 1, and that's why it's when you subtract by 1 that this happens. If you have some positive number that's less than 1 and you subtract by 1, you don't get a positive number. So for all the z's from c to negative c, right? Because when is this thing less than 1? It would be from something smaller than c. So any of these numbers to something bigger. From a c with a, oh, it's also squared. So it happens to be. So that's why we have this side too. Okay, any questions about any of this? Is it clear?
Do you mind explaining what happens when c is smaller than 1 again?
So now when z over here, when we have this equation over here, so that would mean that z is less than or equal to c and bigger and equal to negative c. Sorry, negative c. So for any of these z's, if you plugged it in to this, you would get that this thing is less than 1, right? Because you're having some number that's less than between negative c and c, right? If it's less than or bigger than negative c, but not that small, then when you square it, you're going to have a number less than 1. And if you do, then this side over here is going to be negative, because you're going to have a number less than 1 minus a bigger number, 1. And so this side is going to be negative, but this side is positive. So these sides are never equal. So you don't have anything. And as you can see, it's just blank over here, from here to here.
I see, that makes sense. Thank you.
Okay. Any other questions? Hey. So now they ask us to trace the hyperboloid of one sheet and determine its traces. And again, you can see it's a hyperboloid of one sheet because there's a positive one over here. Okay, so again, if the z direction is going to be the direction with your ellipses. And as this thing, as z is equal to different numbers, you're just going to get different ellipses. So when z over here is 0, you just get 1. So in the x direction, and the y direction, you get an ellipse. This over here is going to be 2. This is 3, and you get an ellipse like this. And as you continue, as the z over here gets bigger or smaller, these ellipses grow, and you also go up. So they're growing. Now this picture's not gonna be great, but it's gonna maybe get the point. But it should kind of start looking like this. Well, maybe, well, anyway. Now, so that's this. So those are the ellipses. And 1 second. Oh, and also there's supposed to be this ellipse over here. So that's that ellipse. Can I erase? Nope. Oh, yeah, it's happening. Okay, that's this ellipse right over, right over here, down here, this blue one. So that would be this ellipse. And then you have ellipses. Now, if you set the x0, the x to be constant, then you have a negative over here in the z, and you have this over here. So these are, again, hyperboloids. So they're going to be stuff that go like this. And you'll be able to figure out where they hit our surface, because that it's always going to hit the ellipse, wherever the ellipses are. So for some reason, one second, they're going to go like this. Basically well, they're going to be hitting all the ellipses, but like that. Okay, and those are these over here. And then you're going to have ones coming from here and from here in the y direction. Those are those. And yep, that's basically it. Okay. So now they ask us to find the traces. Oh no, they say this is a hyperboloid. Whatever, show that this hyperboloid has no point for y between negative b and b. So that's exactly what we just did. We said that this thing over here is positive. So this thing has to be positive. So if it's a negative, we don't have a solution. So when is it negative? Well, it's negative when y over b squared is less than 1. That's when it's negative, which tells us that we want y, as long as y is between negative b and b, we do not have any solution. So that's this over here, negative b and b. And that's basically what they did. Here's this equation, and yeah, so we do not want, so there's a hyperboloid of 2 sheets corresponding to y bigger than b, so that's this, and y smaller than negative b, that's that. And those are the 2 sheets. But in between, we do not get any surface, because it doesn't make sense. Any questions about that? Okay, so now let's go on to a cone. So this is the equation of a cone. So the equation of the cone is going to be x over a squared plus y over b squared is equal to c over z squared. Okay. So now, first again, we can notice that as we, as as we change z, and z is different constants, these are again just different ellipses. So as z changes, you get different ellipses, but this has been happening a lot. You don't necessarily know how these ellipses come together to form the shape. And one way to figure that part out is by, you see now there isn't a 1 over here. So let's look in the y direction for a second. Let's set y is equal to 0. So then that would give us x over a squared is equal to z over c squared. And there isn't a plus or minus 1 over here that came up with a hyperboloid. So we can take the square root of both sides. So we get that cx is equal to za. And this is a line. well, if you're in the z direction, you're going to have a c over a over, sorry, c over a slope. And it's, so this is when y is equal to 0. So it's a line that looks like this. Maybe draw it a little better. Yeah. Okay. And yeah, I don't know, something like this. It's a line. And if you, and because this thing is squared, there's also another line in this direction. So let me redraw these just in green. Okay. Now the same exact thing would happen if we set the x to different constants and we looked at these. Again, because there isn't a plus or minus 1 over here. There is a plus or minus 1 over here, we would, when we take the square root, we would start getting hyperboloids, and then we'd have to deal with that. But now we're just getting lines, which is much simpler. So because of this doesn't exist. Okay, now in the, if I set x is equal to 0, then I'm going to get lines in the zy direction. So those would be lines like this. Well, anyway, it's a cone, so I think it would be better if I actually draw a cone and then I trace over it with these lines, because maybe that's getting confusing. So yeah, here it's a cone. And like we said, so one second, x. Okay, so there are lines. One of them is when we set y is equal to 0, and that's this line over here, this line over here, and then yeah, these lines, and then there are lines when we set our x to 0, and that's when our x is equal to 0, and there's something like that, maybe here. Yeah, oh yeah. Okay, something like this. Okay. And here again, you see the lines over here. And you get a cone with ellipses running up and down with the z direction.
Professor.
Yep.
So you said if we set x and y, x or y to a number, we can get hyperbolas. Can you show like how that hyperbola will look like?
Yeah, so if you had you had this over here, but you had like a plus or minus. So let's just do minus. You'd have x over a is equal to the square root. If you're asking for the exact shape, there are all these formulas of how, I don't really know the formulas right now. And I'm not sure they're that relevant, because for us specifically, we know that it will intersect along the circle, so we can get the shape that way. Let's say -1. Yeah, so how exactly to draw this is not something I'm currently able to do. But again, we don't necessarily need to know how to do that right now. You can just follow the, you can make traces with the ellipse and follow down with the hyperbolas. Okay. All right.
Okay, thank you.
So now, okay, so that was the cone. So here's our cone, and the next two shapes that they would like us to remember are the elliptic and the hyperbolic. So one of them just looks like this, and it's fairly simple to understand. And the other one looks like this, and it's a little bit more complicated to understand how this comes up. But these are a little bit easier to understand. So these are the elliptics. And well, if you have z is equal to x over a squared plus y over b squared, and you set the x's or the y to constants, that let's say you set the y to a constant, and then you get z is equal to x over a squared plus y0 over b squared. And this over here is just a parabola in the x, z direction. It's a parabola. This is the one where y0 is 0, and then we get bigger and bigger. So that's in the y direction. Those are these parabolas over here. So again, when we have z is equal to x over a squared plus y over b squared, then when y over here gets different numbers, different constants, you have a parabola z is equal to x over a squared plus y0 over b squared. And these over here are the places that you end up on the parabola. So so you're going to have parabolas like this. Okay, same exact thing happens if I set my x to different constants. So that would be z is equal to y squared over b plus x0 over a squared. So now you have, now we are in the zy direction. And now we have, sorry. And again, we have parabolas that go like this. So in the three directions together, we have, in the xz direction, we have parabolas. In the yz direction, we have parabolas. Now, what happens in the z direction? So as z becomes different constants, these become different ellipses. So we have ellipses. Okay, and that's going to be this shape over here. Parabolas in two different directions and ellipses. Again, sometimes it's daunting trying to remember all of these different equations, but if you just made some traces of this in the x direction, y direction, z direction, you would immediately see that it looks something like this. Okay, and then the hyperbolic, which is a little, it's it's a horse saddle, basically. So it looks something like this. And again, we have a simple direction and a slightly complicated direction. So the simple direction is when the y's over here are 0 or different constants. So then you just have parabolas in the xz direction. And those are these parabolas over here. You see we have parabolas. So this is when y is different constants. Y is equal to 0, y is equal to 1. You get different parabolas. Now in the now when your y is the thing that you think about in terms of varying, and you look at the x in terms of constants, then you get over here z is equal to negative y squared over b, right, plus x0 over a squared. Well, now these are parabolas just going in the opposite direction, the negative parabolas, and this is in the zy direction. So in the zy direction, you're also going to have parabolas, and those are these parabolas. Well, it's difficult to see all of them. One second. Sorry. Those are these parabolas. These are hyperbolas. I apologize. These parabolas, the green ones over here. So this over here. So again, you have parabolas and going in the upwards direction in the xz plane. So in the xz plane, you have parabolas like that. And then in the yz plane, you have parabolas going in the opposite direction. So here's the yz plane, and now you have parabolas going like this. And that changes as the x gets more negative. Sorry, as the x grows, these parabolas go up. So they're actually going up like this. Okay, one second. Okay, here, let's go here. So again, we're looking at the equation z is equal to x over a squared minus y over b squared. So again, in the so here's our axis. In the x direction, so when y is fixed, so now you're moving along the y direction. So when y is 0, this is just a parabola. So it looks like this. Now when y is gets bigger and bigger, this becomes more and more negative. So these become parabolas that go down, but they're still going in the upwards direction. So maybe you have this parabola over here, and then it goes down even more. Okay, now this is in the, so those are these parabolas that keep going down like that. Now in the other direction, when my x's are fixed, we have other parabolas, and these parabolas are going down. So it's these parabolas over here. They're going down, but they're moving in the up direction as we move along our x, as we move along x. So yeah, this picture is not gonna work out, I don't think. Let me just try to draw a horseshoe and see. This is generally the harder picture to draw. It's okay. Nope. We have that. Okay. Not great, I would say, but well, okay. Fine, I'll live with it. So again, we have parabolas in the zx direction. So those are these parabolas over here. And they continue going up, of course, but I'm not going to continue the drawing. And then you have parabolas in the, so as the x's get to vary, so here's your x direction. So as your x's get to vary, these parabolas, they're going to go up, but they're pointing in the downwards direction. So there are these parabolas over here. Let's say this. And this. Now, of course, the intersection here at 0 is going to be just a parabola with no intercept, so it would go through there. So this picture is, again, not perfect, but I think it serves the point. And then we can think about what happens when z is some constant. So when z is some constant, we can move the, let's say move this to the other side. So we get x squared over a is equal to z0 plus y over b squared. And we can now take the square root of both sides. And we again get hyperbolas. And okay, so this is when z is a constant. So that's along this line over here. And we get hyperbolas like this, like that, and like this. And those are actually these things over here. So that would be this, something like that. So that would be part of the saddle. And those over here are these. And that. Okay, and in general, this over here, sorry, no, those are, okay, anyway, regardless. Okay, does that make sense?
Makes sense.
Okay, perfect. So now, yeah, so they're gonna talk about that. And then they say, show that this equation is a hyperbolic paraboloid by writing the equation in terms of the variables u and v. Okay, so you plug it in, you get u squared minus v squared is equal to z. So z is equal to u squared minus v squared. And that is a hyperbolic paraboloid, right? So these are hyperbolic because they have two hyperbolic, one hyperbolic part and they have a parabola part. These are elliptical because they have elliptical and they have a paraboloid. So yeah, this is going to be a hyperbolic paraboloid. 1 second. Okay. Fine. Then they're like, they ask, without referring back to the formulas, use traces to determine the graph of the quadratic surface given by this over here. So that is x squared plus 2z squared minus y squared. X squared plus 2z squared minus y squared, no, y squared is equal to 0. Okay, so let's move the y to the other side. So we have y squared is equal to x squared. And this looks like the cone that we looked at before, but they said we cannot look at the formula. They want us to find this with traces. So here's my no, let me draw this. Okay, here. X, Y, Z. So now when my y is different constants, I get different circles, different ellipses. With that, well, I would have to divide in order to get the radius, but I don't think that matters. The shape would definitely look like different ellipses. So you would get different ellipses. But like we said before, you don't always know what happens. We know that in the y direction, as we go up and down the y direction, this thing will have ellipses. But how exactly they look, we're not really sure. So let's try to set z, for example, to be a constant, and we are going to get so yeah, when z is equal to 0, we're going to get y well, 1 second. Yeah, well, okay, so we're going to get y if the z is 0, we're going to get y is equal to x, and we're going to have lines and that would be so yeah, a line like this. Okay, we're out of time, so I'll continue this next time. But yeah, any questions?
I had a quick question before you go. For the exam one materials, there was like you put up a bunch of videos from, I think it's a different professor. Is there any way that we can find those videos online? I was just wondering.
I'm not really sure. I don't know. I
Oh,
mean, yeah, there's a link to them, which I gave you. I don't know where you can look for them exactly.
okay. Thank you.
Yeah. Any other questions?
Can you just quickly go over the difference between hyperbolas and parabola?
The elliptical one?
Not really, like just parabolas and hyperbolas in general.
Okay, so yeah, next time I'll just go over that, okay?
Okay, thank you.
Any other questions? Okay, perfect. So see you next time. Bye.